So picture this. You're staring at a completely blank passcode screen on a new device, and you just kind of wonder how many combinations could actually exist here. Let's say you have 5 unique digits to choose from. Just 5. How many completely different passwords can you create from just those numbers? Does the number of possibilities just keep expanding infinitely? Or is there a hard mathematical limit? We face this exact puzzle almost every day in our digital lives. Yet for a lot of us, the math behind it feels, well, a bit like magic.
Welcome to The Explainer. Today we're taking the guesswork out of probability and statistics. Our big overarching goal here is to turn what seem like incredibly complex counting problems into intuitive, easy-to-understand building blocks. Whether you're trying to figure out password combinations or calculate the exact odds of a specific event occurring, mastering these simple mechanics will give you a tremendous analytical edge.
All right, here's our structural roadmap for today. First, mapping all possibilities. Second, understanding events and vens. Third, the multiplication rule. Fourth, permutations and factorials. And finally, counting with constraints. Let's get right into it. Part 1, mapping all possibilities. This brings us to an absolutely fundamental concept, and that is the sample space. By definition, a sample space, which we usually just represent with the letter S, is the set of all possible outcomes of a statistical experiment. Think of the simplest experiment you can possibly run. Flipping a single coin. Your sample space there is just 2 outcomes, right? Heads or tails. Every individual outcome inside the space is called an element or a sample point. It's basically the absolute boundary of what could happen in our specific scenario.
Okay, let's dive into this. This is where things start getting really fascinating. What happens if our experiment gets a bit more complicated? Let's say we flip a coin. If it's heads, we flip it again. But if that first flip is tails, we roll a 6-sided die instead. By drawing out a branching path, like a tree, we can visually trace every single scenario. The top branches show us heads, and heads, tails. The bottom branches show tails paired with each number on the die, all the way from 1 to 6. By literally tracing these paths to the very end, we completely map out our entire sample space, giving us exactly 8 unique elements.
Part 2, understanding events and vens.
So, moving from the big picture to something more specific, we have events. An event is simply a subset of a sample space. Going back to our trusty die, the sample space is 1, 2, 3, 4, 5, and 6. But what if the rules of the game say you only win if you roll an even number? Your event is just the subset containing 2, 4, and 6. It's really just a zooming in, filtering the entire universe of possibilities down to the exact conditions we actually care about. Now, when we start tracking multiple events at once, we need to know exactly how they interact with each other. And this is where the concepts of intersection and union come into play. The intersection of 2 events, let's just call them A and B, includes only the elements that are common to both events. It's the overlap. The union, on the other hand, well, that's a much wider net. It includes all elements that belong to event A or event B or both.
And this brilliantly illustrates how we visually map those overlaps. Here we have a Venn diagram where the sample space is represented by the rectangle, and our 3 specific events, A, B, and C, are represented by circles. Notice how they overlap? If we want the intersection of all 3 events, meaning an outcome that perfectly satisfies the conditions for A, B, and C simultaneously, we look right smack in the center, region 1. Venn diagrams are honestly just a fantastic tool for making sure you aren't accidentally double counting elements when your conditions start getting messy.
Part 3, the multiplication rule. So, drawing trees and circles is great, but to understand how we skip drawing massive diagrams and calculate outcomes rapidly, let's look at a super relatable real-world puzzle. Meet Sam. Sam is building a custom computer and needs to buy parts, and he has a few choices for each component. The question we need to answer is, how many totally different custom computer builds can Sam potentially create from his available options?
Let's break down Sam's exact choices step by step. In step 1, he has to choose from 2 different chip brands. For step 2, he has 4 different hard drive options. Step 3 offers 3 types of memory. And finally, step 4 gives him 5 different accessory bundles to pick from. Think about that for a second. Imagine drawing a tree diagram for this. It would literally be an absolute nightmare of branching lines.
But thankfully, instead of drawing, we use the generalized multiplication rule. The absolutely crucial takeaway here is this. If one operation can be done in a certain number of ways, and a second in another number of ways, and so on, you simply multiply them together.
For Sam, that's 2 times 4 times 3 times 5. That equals 120 completely different ways to order his computer parts. No tree diagram required. It's a massive shortcut that lets us navigate complex combinations instantly.
Part 4. Permutations and factorials.
This brings us to permutations. A permutation is an arrangement of all or part of a set of objects where the order is strictly important. To calculate this rapidly, we use something called a factorial, which you'll see denoted by an exclamation point. Don't let the math jargon intimidate you. A factorial just means you take a number and multiply it sequentially by every whole number, counting all the way down to 1.
Let's actually put this into practice to see how factorials organically emerge. Imagine you have 5 friends, and you want to see how many different ways they can sit in a row of 5 chairs at the movie theater. For the very first chair, you have 5 people to choose from, right? But once someone sits down, you only have 4 people left for the second chair, then 3 for the third, and so on. This is naturally 5 times 4 times 3 times 2 times 1, or written much more simply, 5 factorial. And 5 factorial equals 120 different seating arrangements for just 5 friends. Crazy, right?
But what if you have more objects than you have available slots? Say those same 5 friends, but they show up and there are only 3 available chairs. This is the formal theorem for permutations of n distinct objects taken r at a time. Basically, the formula takes the factorial of your total group, so n factorial, and divides it by the factorial of the group that gets left standing. In the case of 5 friends and 3 chairs, the math simplifies down to 5 times 4 times 3. That leaves us with 60 different possible seating arrangements.
Part 5. Counting with constraints.
All right, time to introduce the what-if twists. Here is a classic constraint puzzle. You have 7 books to arrange on a shelf, but there's a catch. 2 of them are math books, and they absolutely must be kept side by side. How does grouping these items completely change the math we just learned?
The trick here is to change how you look at the objects. Without any restrictions, 7 books is just 7 factorial. Boom, done. But because the 2 math books must stay together, we're going to treat them as a single movable block. So now we only have 6 items to arrange, the 5 single books plus our 1 math block. That gives us 6 factorial. But wait, inside that math block, the 2 math books can actually swap places with each other, which is 2 factorial. So our final calculation is 6 factorial multiplied by 2 factorial. By treating grouped items as single blocks, you can seriously conquer almost any arrangement puzzle.
Now, what's really interesting about this slide is how drastically constraints can reduce your possible outcomes. Look at this setup. We have 5 digits, 1, 2, 5, 6, and 9. If we form a 5-digit number with no repeats, that's 5 factorial, or 120 numbers. But what if we throw a wrench in it? What if the number absolutely must be even? For a number to be even, it has to end in an even digit. Out of our pool, only 2 and 6 are even. This means our last slot only has 2 options. The remaining 4 slots get filled by the remaining 4 digits, which is 4 factorial. So 4 factorial times 2 leaves us with only 48 possible even numbers. Just one little rule cut our sample space by more than half.
Which brings us to our final provocative challenge, straight from the source material. What if repetition is allowed? Using the digits 0, 1, 2, 5, 6, and 9, how many 3-digit numbers can you form that are strictly greater than 199? Think carefully about the constraints here. Which specific numbers can go in the very first slot to guarantee it's greater than 199? And how does allowing repetition change your math for the remaining slots? I'm going to leave you to ponder that one. But by breaking down constraints logically, just like we've done today, you absolutely have the tools to figure it out. Thanks so much for joining me on